So this problem is not technically plane stress, but we can call it plane stress if the thickness or the width of the beam is relatively small compared to the depth 2C or 2H here. So we got some boundary conditions. Let's just take a look at those. At y equals plus C or minus C, the shear stress is 0, good. At y equals plus C or minus C, the sigma y is 0, very good. And at x equals 0, sigma x, pushing left and right, is 0. We got air out there, okay? Good. So we begin with sigma x is minus pxi over y. Take a look at the signs. Hit the pause button if you don't understand the signs of this. We're looking for tau xy. We're looking for sigma y. But we know that, and then we need the displacements. So you start with your boxed equations way back when, equation 2.4-2a. And these are the equilibrium equations, but they're in their unusual format where you're differentiating stresses to describe forces. So partial sigma x plus partial tau xy partial y is equal to 0. And we're going to lift out those functions just like we did before. And then the second equation is 2.42b, excuse me. So I want to start with this second function here. And this is pretty interesting here. What does this second line here tell us about tau? Now think hard about that. What does this second line tell us about tau? Because we know something about sigma y. What do we know about sigma y? Sigma y is 0. So the second line tells us that if this is 0, then partial tau xy partial x is equal to 0. Therefore, tau xy can only depend on y. This is a very subtle but very important idea. Tau xy does not change with respect to x. Let me say that one more time. Tau xy does not change with respect to x. And think about what that means in this problem. It's saying that regardless of where I am on any x cut, the shear stress is not a function of x. Does that make sense? The shear force certainly doesn't depend on x. Therefore, the shear stress does not depend on x. It does depend on y, though. Okay? Obviously it does. It's the parabolic distribution with respect to y. So here we have our subtle but super important switch that d tau xy dy becomes a regular derivative instead of a partial derivative. So we can go back to the first equation in here and switch this partial to a regular. So I have partial sigma x partial x plus d tau xy dx is equal to 0. That's a terrific expression. And then I integrate, I lift out the tau xy, picking up a constant here instead of a function. And how do I get the constant of integration for this type of equation? It's a boundary condition, but what kind of a boundary condition? It's a boundary condition on stress, not on displacements or rotations. So we could use the top or the bottom of the beam. The stress is 0, and I can get C1. And put a box around this and even put a little tab on this part of your notes here. Tau xy is minus p over 2I times c squared minus y squared. Super important equation. Make sure you understand this derivation inside, outside, upside down. Okay?